one. So this is just kind of like a little like set of like tips, or just kind of like a little explanation as to um not being as like intimidated by numbers and math and stuff. So this is obviously geared more towards like lower level concepts. Um, but many people I know say stuff like, "Oh, I can't really wrap my head around numbers. How do you know how to do that?" and stuff like that. And I think part of this kind of like disconnect comes from maybe not knowing why numbers work the way they do, not understanding our number system, the decimal number system, and how that kind of is. And and this thing I kind of like to kind of call it like the fluidity of numbers, or like the fluidity of equations, because I think people see like big numbers or weird equations, maybe like and then their brain just shuts off, right? Now, this I couldn't really just solve right in my head, right? But but things like this actually tend to be easier to work with than one might realize. So, for example, and this kind of goes back to the fluidity of numbers thing I was talking about, is that this isn't even really a number, rather than that it's an equation, right? And what I mean by that is going back to explaining our number system. So how about I explain that first, right? And then I'll go back to this. So I'll just hide this right now, right? And so our number system, right? It's called the decimal number system. That's because we have deci 10. We have 10 digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And so, 1, 2, 3, there's 10 of them, right? Decimal. And that's probably because we have 10 fingers. As to why that's where we stopped at. But so preface, I think here in the United States, there's like, I don't like this joke. I think it's kind of mean spirited. It's really more of a stereotype, but that Eastern Asians are better at handling math, and that's because if you're familiar with those number systems, for example, what is it? I believe 14. Let me do 13. I forgot how to write 4, but 13 is this, right? And it's quite literally 10 3, because all 13 is 10 plus 3. And so what you'll see here, though, is that there's kind of a positional thing going on here, right? So, because for example, then 30, using like the Chinese characters, right, which they also use in Japanese and whatnot, but 30 then is just this, right? And what's going on here? So we have it's literally 3 times 10 plus 3. And that's because there's like a positional thing going on here. Maybe this wasn't the greatest example, but they kind of learn a relationship between where these things are placed, which is important when you realize that a number is really more of an equation, like I was saying. So in our case, we start from right to left in precedence, and that, what I mean by that is, really what we have going on here is we have 10 digits, right? So or maybe this is really more of like I guess I don't really need to put the x at all. So let me just do 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. Now, if you've ever counted in binary, you should already understand this, but why are these here, right? So obviously 10 is here because we have, like I said before, those 10 digits, we have the decimal system. But what's with these powers, right? So let me show you something. This number right here is 1, right? I don't think I need to explain the value of 1, but I think we could all agree that 1 is the same thing as 1 times 10 to the power of 0. Now, why is that? Well, 1 is the same as 1 times What is 10 to the power of 0? Well, anything to the power of 0 is 1, right? What is 1 times 1? 1. So 1 is equal to 1. Okay, now hold with me. Same idea here. Let's say I put 4, right? 4 equals 4 times 10 to the power of 0. Is this true? Yes, because 4 is equal to 4 times 1. So what's happening here is that really, if I were to show you now the number 13, right, is just like I showed before with 3 and 10 to the power of 0, right? 3 times 10 to the power of 0 is the same as 3 times 1, which is the same as just 3, right? Well, now here we have 10 to the power of 1, right? So, and right here we had a digit 1. So 1 times 10 to the power of 1 is 1 times 10, which equals 10. Well, as it happens, 10 plus 3 is 13. So what we really have whenever we have these numbers, right? If I erase these charts, what is this? This is 13. Well, this is how all of our numbers work. All of our numbers are really, like I said before, an equation, because all that we're doing is adding these products, right? And so going back to that concept of how numbers are really an equation, this I can't do very easily off the top of my head. But what if I did this, right? 163 is actually the same thing as 162 plus 1, right? And so now what if I had 162 plus 1 plus 58, right? Well, this is easier because I can work with the 2 and the 8, right? And so I know what I really have is 160 plus 60. If I just move this 2 over here, right? Let's add this 2, and to keep everything equal, I take 2 away from this, right? Plus 1. Well, I know that 160 plus 60 is 220. And I still have that plus 1, so it's 221, right? And so before, I would have had to kind of think a little bit harder about this 163. But since I acknowledge that numbers they're fluid, right? And they're really equations, I knew that 163 doesn't have to be 163. I could make it 162 plus 1, or 161 plus 2, or 164 minus 1, right? Whatever it is that helps you to work easier with these numbers. And so this same idea of fluidity applies to fractions, right? I think often people end up thinking of fractions as numbers, right? Fractions are equations. And so I guess if I'm going off what I said earlier before, that numbers are really equations, then then they're right as well. But I think that when you see something like this and getting confused, instead maybe it might be more helpful to think of this as an equation. I mean, it's quite literally 5 over 2, or in other words, 5 divided by 2, right? And so obviously this one is pretty easy. Everybody knows that half of 5 is 2.5, but so take away 2, 4, 0 drops down, right? And 5 minus 10 is 0. So this is it's the same idea, right? I remember I have already taken all these calculus and discrete math classes, and but my friend had he's not really doing like a STEM major, so he was taking a math class. I guess he hadn't taken math in a while, and he was like, "Dave, this sucks. Can you help me?" And I was like, "Yeah, of course, no problem." And I saw particularly though he would see like a really weird fraction like this, right? And he'd just be like, he'd be tripped up by it, and I was like, you don't have to do that, because this is just an equation. Like whether or not it's surrounded by all this other nonsense is irrelevant. This is it's fluid. You don't have to write it like this. You can figure out whatever it is. You can even write this as if you wanted to call it z to get it out of your head, so long as you remember what z is equal to. But I thought it was kind of telling that he couldn't get past this because he's like, I need to know the value of this. But really you could have just went ahead and just went about solving it or ignoring it or writing it a different way. So for example, I mean, again, 63 is really 62 plus 1. If you divide this by 4, and so then, or maybe a better way might be 63 is really 60 plus 3 over 4. Well, they have a common denominator, so what you could really do is 60 over 4 plus 3 over 4, because these two are equal, right? And I think a lot of us know already that 60 divided by 4 is 15, and this is also commonly known as just being 3/4 is 0.75. So there's a solution to that, and I didn't have to finish all of this. I just did it right in my head, and that's and I could do that because I know that these things aren't rigid. These can be moved around. These can be broken down into smaller parts that are easier to work with, and you can keep breaking them and rearranging them, so long as you're being attentive to keeping balance. You know what I mean? Again, I can't just get this 60 and ignore this 3. The 3 still has to be there because that's just one of the many equations for 63. 63, we think of it as a number, but I mean, again, really it really is like infinite combinations of numbers, and that's because there's infinite ways to make decimals, right? For example, I could do like 62.9 plus 0.1, and then I could just do this forever and ever and ever, changing how I move the decimals around. This can go on for eternity. So I just thought that's maybe a thing that people don't take into consideration when they're working with numbers, and it's not your fault, obviously. Somebody has to teach you. If they don't teach you in a way that clicks with you, they don't spend enough time with you, etc. Many different things. People's brains are structured and ordered and all sorts of different things. But I thought this might be a helpful thing to for anybody out there who just kind of sees math and numbers and just goes, "Oh my God, not again." You know what I mean? Because I personally, I love math and puzzles and stuff like that. I think it's really cool. So yeah, I thought this would I just thought this was a thing that might maybe help somebody out there. It's a little bit maybe aimed more for like younger children in their classes who just needed something to kind of get them by. But yeah, I hope you enjoyed this.